Neurips 2024, part 13. This paper is very close to the paper just discussed before. DreamDrive generative 4D scene modeling from street view images. So this is similar to Memorize What Matters, emergent scene decomposition from multi-traverse, the one we just discussed before. Because what this paper does, it builds a model that takes images and then projects in 4D based on self-supervised learning. So no annotation, none of that. I think this is, we've been talking about this for years, that this is the holy grail of simulation. This is the holy grail, in my opinion, of any kind of robotics model, because what you can do is you can see the world and then project the future, either as a simulation method, or you can use it actually for planning, because you could extrapolate the next couple of time steps and then act accordingly. And then if reality is different than what you're extrapolating, you can adjust your actions, or you can learn from there. So this paper is pretty crucial in that context. Again, so what they're actually using it for is for self-driving applications, but I think this can also be used for for simulation. So the idea is the following: like you want to take ego images, 2D images, and turn them into 4-dimensional videos. And what does that mean? First, you have to go from 2D to 3D. And the way they do this is they use a diffusion prior. So they take an image and then they use diffusion to generate potential future images. But what's important here is they don't stop there. They use Gaussian splatting to turn it from 2D into 3D, which in particular uses depth information that can be learned, or it can be annotated, or both, by understanding the camera pose. By having stereo cameras, you can extract depth information and then turn 2D into 3D. And then the interesting thing from going to 3D to 4D is they're decomposing static and dynamic Gaussians by looking at basically running an algorithm that optimizes for image reconstruction from time step to time step. And whatever errors happen, that is the difference, is the dynamic part of the image. So from there, you can then learn, again, the Gaussian parameters that apply to the dynamic pictures versus the ones that are static. And assuming that most of the Gaussians that move in the same way also belong to the same object, you can then also segment objects. So this is roughly the outline of the paper. The links in the show notes, it's pretty technical. And I don't want to do the authors an unfair service here by trying to explain what they're exactly doing in terms of technicalities. I think it would be unfair also to the listeners. I am not in that business. What I'm trying to say is here, first and foremost, this is a Neurips paper, so it's important to understand what's being presented at Neurips in terms of what's really hot right now. I think this paper is certainly not the most original paper. We've just seen, let's say Pavone's team has done similar work in trying to dissect dynamic versus static. And we can also go further and ask ourselves, okay, what matters in the picture versus what doesn't matter? It's not necessarily dynamic versus static. What really matters in robotics in general, or self-driving in particular, but let's just say robotics. We just throw in self-drive with everything else that moves in the physical world. So in robotics, what we try to really understand is what matters in the image and what doesn't, and what the trajectory is going forward, which trajectory matters for our action planning. That's really important. So when we have a flag that's waving, which is a dynamic process, but the flag is static and the waving is kind of predictable also, then maybe we can learn that also in an end-to-end context, and therefore disregard the flag and not worry about it. Versus if we have a dog or a child that is next to the road, that is certainly something we want to worry about. However, if we can also have pose estimation, understand that the dog might be turned around and facing away from the road, then that's maybe less dangerous than if the dog is facing the road. So those are the kinds of questions that I think that's what we're really trying to do, is connect the dots, see between the papers and between the research projects where the field is going. And I think the field is going towards this learnable, end-to-end, self-supervised reconstruction of the reality from 2D into 3D, and then applying to 4D, which just really means, again, having a time, time. I mean, more than one time step, right? And the fundamental idea behind dynamic versus static objects is twofold. One is Gaussians. So once we dissect the image into Gaussians, we turn it into a 3D. So all these Gaussian points, or the splatted image, if you will, all these Gaussian points with their parameters now, they represent a 3D image in static space. And now we add the time component. What we're going to have is Gaussians that move together and Gaussians that don't move together. Certain, of course, positioning, the positioning relative to the camera pose, things like that will move. And the Gaussians that move together belong to the same object. So this could be also used for object segmentation. I think that's really the most interesting engineering aspect, if you will. It is this insight that Gaussians first turn the image into Gaussians, have the right parameters, because these Gaussians, you can have just position and depth, but you could also have color, lightning. You can use lighting. Not lightning, lighting. You can use lighting as a proxy for movement. So there's a lot of engineering tricks that you can play and hacks that you might use to extract information from the image. I think that goes beyond this paper, and that's part of the discussion. But fundamentally, what you're trying to do is, again, you're trying to first represent the image in appropriate Gaussians, and then use the difference between the Gaussians that are the same over several time steps and those that aren't, to then segment the image into static and dynamic, and use the dynamic part as the 4D implementation, or in other words, when time steps vary. So to summarize again, the DreamDrive is, I think, an important paper in two contexts. One is, how can we simulate reality more efficiently? Well, we can have a self-driving car drive, take 2D images, and we can then use those to train a 4D generative model and generate many trajectories over the same road, and then train the model in sim. And we can also use the generative 4D model for the actual planning in a context that if we are facing a situation, and then we have a generated next few time steps, and then we have a discrepancy between what's generated and what's real, then that can be used for planning and for learning, and or for learning. Thank you.